Hello students, welcome back to the class, and we will continue our discussion on the first law of thermodynamics, and the topic of this lecture is enthalpy. So enthalpy is the second energy function which is encountered while dealing with the first law of thermodynamics. So how does the concept of enthalpy come out from first law of thermodynamics? For this purpose, I will revisit the experiment that I have discussed while studying the variation of internal energy with temperature in the experiment where we discussed heating at constant volume. And here we showed that the change in internal energy during this process due to this process is equal to the total amount of heat supplied to the system under isochoric conditions. Similarly, another experiment can be devised, that is heating at constant pressure. If I schematically show you the experimental setup that is used to carry out such a change in state, as you see that the gas is contained within a cylinder and highlighted using the light blue color over here. As before, the gas is surrounded by insulated walls on this side, as well as on this side, and it is separated from the surrounding by the conducting wall on the bottom. Therefore, if I supply heat from the bottom, heat can be transferred to the system and the gas can get heated up. But the difference between the previous scenario and the scenario that I am presenting here is that now I have on the fourth side of the gas a wall that is adiabatic in nature, which means it doesn't allow exchange of heat across it, but this is movable. And not only it is movable, there is a frictionless and piston attached to it, and by adjusting the mass placed on this movable wall, we can adjust the pressure that is holding the piston down, and at equilibrium that would be the pressure of the gas. Therefore, if now I heat this system, then I will be heating the system at constant pressure. So just as before, if I know the total mass of the gas contained in it, and also I know the mass of the calorimeter, empty calorimeter or the setup that I have here, and if I know the specific heat at constant pressure, and I note down the change in temperature due to heating that can be read out from the thermometer as shown here, then you can calculate the total amount of heat supplied to the system under this experiment of heating at constant pressure. Now the question that I ask here is, in this case, is it possible for me to equate this total amount of heat supplied to the system to some kind of change in a state function, which is also an energy function? And in this connection, we introduce you to the concept of enthalpy in relation to heat transaction at constant pressure. So how is enthalpy defined? The definition of enthalpy is U plus PV. So the sign of enthalpy is H. That is a summation of internal energy plus P into V, where P is the pressure of the system and V is the volume of the system. Since U is a state function, so are pressure and volume. Therefore, H is a state function as well. Therefore, the properties of H are going to be delta H should be equal to H2 minus H1 when the system undergoes a change in state from state 1 to state 2. If I think about the exact differential, d of H is going to be d of U plus PV. This will give me three terms, the first term being du and the second term being PdV and then a third term giving me VdP. So this is all perfect general provided you know the definition of enthalpy H equal to U plus PV. Now if I have a constant pressure process, under that condition, what shall I have? I will have dP equal to 0. So under this condition of constant pressure process, what would be dH? dH now is going to be du plus PdV. That is simply because from this general expression, now VdP is 0. And now dH by the first law of thermodynamics is nothing but the infinitesimal amount of heat exchanged between the system and the surrounding during the constant pressure process. And therefore, if I have a finite isobaric process, I am going to integrate dH from the initial state 1 to final state 2, and then this would be given by the change in enthalpy as the system passes from state 1 to state 2, and by definition this is going to be H2 minus H1, and this would have a magnitude of this integral. And what is the magnitude of this integral? The total amount of heat exchanged between the system and the surrounding during this finite isobaric process. Therefore, what I understand is if I want to find out the value of change in enthalpy, this is equal to the amount of heat exchanged during the change in state under a constant pressure condition. So now if I go back to the previous experimental situation, I understand that when I heat the system at constant volume, delta U is equal to the amount of heat exchanged between the system and the surrounding under such isochoric condition. On the other hand, if I am heating the system at constant pressure, then I find that the total amount of heat supplied to the system, that is equal to delta H, or change in value of a new energy function H, where H is U plus PV. Now the concept of enthalpy and heat has been known in the literature of thermodynamics for a very long time, and so people devised many different ways, some more accurate, some less accurate, to find out QP, that is the amount of heat exchanged during the constant pressure process, and hence probe the change in enthalpy during a given change in state. So here are some pictures of some of the apparatus that are routinely used to find out delta H for a given process. And these are usually isobaric calorimeter, which are available even in the simplest of the laboratories. But if you want a more accurate and much more advanced level of measurement, then you would probably be working with a differential scanning calorimeter or an adiabatic flame calorimeter, of which a schematic diagram has been presented over here. Now, most of the times what happens is you do measure the property of a system called the molar specific heat at constant pressure, which by definition is given by this expression. Therefore, if I have a constant pressure process, then I will say that for an infinitesimal change in state, dH is going to be Cp molar multiplied by dt. In many cases, especially for complex systems like solids, you find that this molar specific heat is in general a function of temperature. So what you do is you find out this CPM and at different temperatures, and you fit it to an equation like this. So for different substances, these constants A, B and C are going to be typical characteristic constants of the system that you are studying. And then you can find out delta H by using an expression like this. If for a given substance the molar specific heat is independent of temperature, then you can take this term out from the integration and say that, okay, in that case delta H is going to be NCPM into delta T. But in many cases, as I've already mentioned, that Cp molar is a quantity which depends on temperature, and therefore one has to explicitly know the molar specific heat as a function of temperature to be able to evaluate this integral and hence find out what delta H is. Now that we have understood how to measure enthalpy for a given process, let us now go over and see how we understand the enthalpy of an ideal gas. So by definition, dH is equal to du plus d of PV. For an ideal gas, I know that PV is equal to nRT, that is the ideal gas equation. If I put it back together, since R is a universal constant, therefore I must be having dH equal to du plus R into d of NT. Therefore, dH is distinguishable from du by this term d of NT. And this term will be different for different processes. For example, if I have an ideal gas undergoing an isothermal change in state. So what is d of NT? D of NT, that is equal to T into dN, T into dN plus N into dt. So if I have an isothermal change in state, then dt goes to 0. So what should I be left with? I should be left with an expression like this, such that for a finite process, I can say that delta H is equal to delta U plus delta N into RT. So what is delta N? Delta N is the change in the number of constituent particles, and delta N will be given by N2 minus N1, when this is the number of particles in the initial state and this is the number of particles in the final state. We can also have some other situation when I have an ideal gas undergoing heating or cooling in a closed vessel. So in that case, I cannot say that dt goes to 0 because I am heating the system, but it's a closed vessel. So under that condition, dN will be equal to 0. And so I should be able to write that dH is equal to du plus nR dt. So if I now integrate on both sides between the initial state to the final state, what shall I get? I will be integrating from T1 to T2 for the second term, and therefore what I would get is delta U is equal to delta H is equal to delta U plus nR into delta T. Now since it is an ideal gas, we have already seen that delta U is equal to NCVM into delta T, right? Or if I represent NCVM as just CV into delta T, then I can very easily write that delta H now is CV plus nR into delta T. And what is that quantity? That must be Cp into delta T, where Cp is the specific heat of the n moles of the substance, n moles of the ideal gas which is undergoing heating or cooling in the closed vessel. So delta H is Cp into delta T for an ideal gas. Now let us look into further variation of enthalpy with system variables, and therefore we have already talked about how enthalpy varies with temperature at constant pressure and how this variation is quantified in terms of the specific heat at constant pressure. The next one that I highlight over here, that for a closed system in general, I can write enthalpy as a function of temperature and pressure. And therefore, I can say that dH would be Cp dt plus del H del Pt into dP. So once again, I am talking about an initial equilibrium state which is temperature and pressure of this closed system. So N is a constant. And I understand that since H depends on T and P, therefore it will have certain value H for this initial equilibrium state. Now I make the system undergo a change in state, whereby the new equilibrium state is characterized by a temperature T plus dt and P plus dP. For this final equilibrium state, what will happen to the value of H? H will now take up a value of H plus dH. So we are asking the question, if the temperature has varied by this amount dt and if the pressure has varied by this amount dt, what would be the corresponding variation in the value of H, and that is dH. And in general, dH is given by this particular expression. I have already mentioned that the Cp values of different substances are already quite well known in the literature, and therefore if I can find out what this quantity is, I should be able to find the change dH for any change in dt, any change in temperature and pressure of any given system. In order to evaluate del H del Pt, now we have basically we are looking at the variation of enthalpy with pressure at constant temperature. Let me start from this equation once again. I want del H del Pt. So I use the chain rule once again and write down the chain rule for involving this partial differential equation. And so if I rearrange these two things, this equation, I find that del H del Pt now depends on two partial derivatives. Of these, one is a partial derivative that we already know, that is del H del Tp, which is nothing but Cp. So there is another partial differentiation that I find here. I will call it mu Jt. So what is mu Jt? This is another response function which is known as the Joule-Thomson coefficient, and it is a characteristic property of the system that you are studying. Now if I go back and see in what kind of experiment can I measure the mu Jt, I find that I must be varying in that experiment the pressure of the gas, and I should be recording the resultant change in temperature of the gas. But I will have to carry out this particular experiment under certain very special conditions. And that condition is I have to do this under constant enthalpy condition. So the Joule-Thomson experiment actually allows you to measure mu Jt under this special isenthalpic condition. So let's see how this experiment sets this very special condition up. So for this purpose, this is the initial equilibrium state. I have a gas which is shown in this pink compartment. It is contained within this compartment and it has a surrounding which is adiabatic in nature. On one side, on the third side, I have a piston which pushes this gas and maintains it at a constant pressure P1 at a temperature T1. On the fourth side, I have a porous plug. And on the other side of the porous plug, I have another piston which is held here by applying a constant force of P2. Now, if I perturb this system and allow the gas to expand through the porous plug from the left-hand side compartment to the right-hand side compartment, then this is going to be my final equilibrium state. So what has happened here? When I kept on moving the left-hand side piston over here, the gas started getting compressed against this constant external pressure of P1. And I made sure that it is an isothermal compression. And then the gas is compressed and its volume will change. Why should its volume change? That is because the gas will escape through this porous plug. And therefore, between the initial equilibrium state and the final equilibrium state, the volume of the gas contained on the left-hand side compartment of the porous plug, that will go from this value V1 to 0, and this is where the volume of the left-hand side compartment containing the gas is equal to 0. Now, what has happened to the compartment 2? In the compartment 2, which is present on the right-hand side, I see that after crossing the porous plug, the gas in the compartment 2 would expand against a constant pressure P2. Now, the experiment is carried out in such a way that P1 is greater than P2. And therefore, what will happen? The gas will flow from the region which is on the left-hand side of the porous plug, which is my compartment 1. It will flow from here, which is a region of high pressure, to the right-hand side of the porous plug, which is this, and this is the pressure. It is going to the region of low pressure. And also, the boundary of the system moves with the gas and it would enclose the same mass of the gas. So this is a very clever design of this experiment, which says that I will drive the gas from the compartment 1, that is on the left-hand side of the porous plug, and while I am compressing it, I will keep on moving this piston in such a way that the gas, it escapes through this porous plug, goes on the other side, but the boundaries of this system, which are indicated by the two pistons on the two sides of the porous plug, would enclose the same mass of the gas. So, can I talk about what is going to be the initial and the final equilibrium state in this during this change in state? So, the process that I have carried out in compartment 1 is an isothermal compression under constant pressure P1. Compartment 2, I saw the expansion of the gas against a constant pressure P2. Therefore, if I look at the compartment 1, which is the compartment left of the porous plug, the initial state is characterized by T1, the volume of the gas V1, and n number of particles. And if I look at what has happened to the left compartment, I find that Finally the volume is equal to 0 and n is also equal to 0. But in my experiment, I would like to focus on the right hand side compartment, or compartment 2, in my schematic diagram, whereby the final equilibrium state is characterized by a temperature T2, a volume V2, and the same number of particles N now present on the right hand side of the compartment. And therefore, our question would be that this transition from this initial equilibrium state to this final equilibrium state of n molecules or n atoms of the gas, from a region of high pressure to a region of low pressure, what kind of process is this? I wanted to have an isenthalpic process. So we are going to find out if this process is isenthalpic or not. To understand this, this is what we derive from this experiment by the design of it. This entire experiment was carried out under adiabatic condition. Therefore, Q is equal to 0. Then the first law of thermodynamics tells me that delta U, which is U2 minus U1, that must be equal to W. Now what is this W? W must be equal to W1, that is the work done during this change of state in the compartment 1, that is in the compartment on the left hand side of the porous plug, plus W2, which is the amount of work done in the compartment 2 on the right hand side of the porous plug. Now what is W1? In this case, W1 is compression of the gas against a constant external pressure, whereby its volume goes from V1 to 0. So what is P external here? So W1 must be P external into V final minus V initial. Here P external is P1, V final is 0 and V initial is V1, and therefore W1 is equal to plus P1 into V1. Now what is W2? W2 is minus P external into the final volume it attains minus its initial volume, and here P external is P2. Therefore, this is P2 into V2 minus 0, because on the right hand compartment I started from a 0 volume of the gas and I ended up having a volume V2, and this expansion was carried out against a constant external pressure of P2. Therefore, I can find out W2 is equal to minus P2 into V2. So what is W? The total W in this case therefore turns out to be P1 V1 minus P2 V2. Now if I want to combine this expression to this expression, what should I get? I get U2 minus U1, that is equal to P1 V1 minus P2 V2. And if I rearrange, what do I get? I get U2 plus P2 V2, that is equal to U1 plus P1 V1. And what does it mean? It basically means that whenever I am saying that U2 plus P2 V2 is equal to U1 plus P1 V1, then this quantity is nothing but H2 and this quantity is nothing but H1. Therefore, in this very clever design of Joule-Thomson experiment, we have studied the isenthalpic expansion of a gas from a region of constant high pressure to a region of constant low pressure through a porous plug. And here, if you measure the change in temperature delta T, then mu Jt can be estimated for the given gas as delta T by delta P by carrying out the Joule-Thomson experiment. In my next lecture, I will take up from here and tell you about how to use the results of Joule-Thomson experiment in real life. Thank you.